Half-life problems. I actually enjoy half-life problems to a great degree. And a lot of the kids do too, because they're really not that bad. I don't think they're that bad, but that's me. So what is half-life? Half-life is how long it takes a substance to transmute into a different substance. Or when you talk about maybe medicine, how long it takes for your body to discharge to some degree the medicine that you take. But a lot of these half-life problems deal with radioactive material. The isotope changes to something that's less radioactive. You're not destroying matter, you're losing energy and you're changing into something else. But to transmute, which means to change, you guys should be familiar with some of that vocabulary. All right, carbon-14, which is a radioactive decay, a radioactive isotope of carbon-14, is often used for geological dating. I've seen some textbooks say it's 5,700 years and some say it's 5,600 years, which just makes the conspiracy theorists and me doubt it even more. But anyways, it has a half-life of 5,600 years. This means that in 5,600 years, half the radioactive atoms in a sample of carbon-14 will no longer be present. What's cool is that all living animals contain the same percentage of carbon-14, and it's assumed that that percentage has always been the same as long as plants and animals have been on this planet. You'll notice I underlined the word assumed. When the sun was younger, it emitted more radiation, and carbon-14 is derived from radiation from our sun. So if the sun goes through peaks of increased radiation, it would make sense to me, but I'm just a math teacher, that this would change. I could be wrong. But anyways, it's assumed. There's an issue. Anyways, there's two ways to set up half-life. One of the ways to do it, which is the way I teach it in Algebra 2, is to use that the amount after time passes is the principal times 1/2 to the t over the half-life time. The other way of doing this is using the principal times e to the RT, which is way harder. And for some reason, it's what your professor in college algebra uses. I don't know why they do that. But anyways, I'm not trying to kill anybody. I'm going to do this one. It's the easiest form to use. All right, so skeletal remains of a humanoid are found. After careful analysis, there is found to be that the percentage of carbon-14 is 10% that of a modern-day human. How old are the skeletal remains? So this is literally the amount left after time passed. So ACE of T is 10%. All right, we'll just leave it as a percentage. It's not a big deal. Now, before the person died, they contained 100% of all the carbon-14 they would have. So my principal is 100%. What I'm writing is a big deal, okay? And the rest of it is just plug into the half-life formula. So the amount after time is the principal times 1/2 to the t over half-life. And it's carbon-14, and we just looked at the notes, it's 5,600 years. So 10%, and I'm going to drop the percentage symbols, equals 100% times 1/2 to the time over 5,600. Now we're going to play the isolation game. We're going to divide both sides by 100, and we're going to get the decimal for 10% here because 10 over 100 is 0.1. And there's lots of ways of doing this problem from here on out. I am going to ln both sides because it's the easiest way to do it. So the natural log of 1/10 is equal to 1/2, oops, without the ln, to the natural log of 1/2 to the t over 5600. Remember, you're allowed to move exponents out front. The natural log of 1/10. And I'm going to do some working with this to make this thing look as pretty as possible, is equal to t over 5600 natural logs of 1/2. Now, my goal here is to isolate that t. So there's lots of things I can do. I can multiply both sides by 5600. That can be one thing I can do. And I will still have t times the natural log of 1/2. So now I can divide by the natural log of 1/2 as well. And here is where I'm really going to make this thing look a lot different. For the average kid, I'm very happy if they can get this far. I really am. Because, the answer is pretty important here. Math num n over d, 5600. And we have natural log of 0.1. And that's divided by the natural log of 1/2. Flat earthers and certain people aren't going to believe that this is the correct answer, but it's 18,602.7973 years. Now, I don't know how accurate this is, but I suspect it's fairly accurate, 0.7973. It's within a few thousand years of being correct, in reality. But I want to play with that answer because there's several of you that are very, very capable of just going to the next level with things. So let's rewrite this. Now, 1.1 is 1 over 10. So you talk about the natural log of 1/10. You'll have 5600. You can break apart division with subtraction. Log of 1 minus log, sorry, not ln. I guess if we log both sides, this is what it would look like. ln of 1 minus ln of 10. Notice the set of parentheses containing that with the 5600. And the bottom would be broken apart as ln of 1 minus ln of 2. This is the highest level answer you can possibly give. You are simplifying, you are breaking things down, breaking them apart. You could even take like this natural log of 1. It's nothing. What is the natural log of 1? It is 0. So you could really make this thing look like negative 5600 ln's of 10 over a negative ln of 2 and then plus plus. Perfect. Like, wow, logarithms. You know how to manipulate them. You can read them and understand them. You are a high-level kid. All right, the half-life of weapons-grade plutonium, plutonium-239, is 24,100 years. Find the yearly decay rate. All right, so I don't know my principal, nor do I care. It's 1/2 to the t over 24,100. So here's a formula. I can move part of that thing in. And leave the t over. And this is what I want to know. I want to know that. 0.5 to the 1 over 24,100. We're going to carry this thing out pretty far because it's radioactive decay. So 0.997123991. 99712. All right, there's no way I'll remember that. 4 9s. 712,391. This, by the way, is still rounded. It is still a rounded number. Now, find the yearly decay rate. Well, This is decay. Decay by default is the principal times 1 minus r to the t. This is why there's a half in there, because we are losing 50%. So 100% minus 50% of half. So we're just going to do this lineup process that a couple of y'all have started accepting in your heart. 1 minus r equals 0.9999712,391. And that's as simple as just taking away from 1. So let's go back to my TI-84, 1 minus that thing. Pretty small, and look at the answer, 2.87609 times 10 to the negative fifth. 2.87609 times 10 to the negative fifth. Now, I know that you're in chemistry. You have to move that decimal 5 places, 1, 2, 3, 4, 0, 0, 0, 0, 2, 8, 7, 6, 0, 9. That's your rate of decay per year. Pretty small, huh? All right, using the original text, suppose 50 tons of leftover plutonium are placed into storage. How long until there's only 10 pounds of radioactive material? Basically eternity. I mean, it's going to be billions of years it's going to happen. All right, so a ton is 2,000 pounds. You probably don't know that because you're the average American kid, but a ton is 2,000 pounds. That is going to be my principal. This is the amount after time, and there's my half-life. So I want to get to 10. I have a principal of 50 times 2,000, 100,000 pounds. And then I have a half to the t over 24,100. Divide both sides by 100,000. Notice I'm not using y1, y2 anymore. So 1/10,000th is 1/2 to the t over 24,100. And the technique here is going to be to ln both sides. The natural log of 1/10,000th is equal to, and I'm going to skip some steps, t over 24,100 natural logs of a half. I hope I didn't throw you off there. I skipped some steps. All right, so I'm going to counteract division with multiplication, and I'm going to counteract multiplication with division. And if I do it to the right, I have to do it over here. So we're going to multiply by 24,100, and we're going to divide by the natural log of a half. Then we're going to go push some buttons, and I'm not going to spend 10 minutes cleaning this up for you. We've got 24,100. It is times the natural log of 1/10,000th. And notice I'm going to press the enter key here. That is divided by the natural log of a half. Oh, that happened a lot quicker than I thought. Only, that doesn't seem right. At all does that seem right. I thought it would be longer. 320,233.8683 years. 320,233.8683 years. That's crazy. So we have 100,000 pounds. We cut it in half, we're down to 50. We cut it in half again. Cut it in half. Cut it in half. It's 1, 2, 3, 4 times I've cut in half. 5 times. 6 times. 7 times. 8 times. 9 times. 10 times. 11 times, 12 times, 13 times. Okay, so yeah. So our answer was, I just thought it would take longer. We have 320, 233. We have a half-life of 24,100. So yeah, it was about to happen the next time, wasn't it? So yeah, okay, the answer is reasonable. I just thought it would take longer. Yeah. Certain drug has a half-life of 11 hours. You are administered 800 milligrams of this drug. You don't want to die, so you hope the nurses and doctors are paying attention to things. Write a model that can determine how much of the drug remains in your system. So this is model writing. The amount of time passes is the principal of 800 times 1/2, simply to the t over 11. Determine how much remains in your system after 16 hours. All we have to do is plug in a 16 and then push some buttons in a TIE forward. Maybe. It doesn't want to come up. Come on, calculator. So we got 800 times 1/2. Rooftopped to the 16th 11th power. That is the 11th root of something to the 16th power. 291.8960 milligrams. 291.8960. 960 milligrams. Convert your hourly model into a minutely model. Well, you don't even have an hourly model. You have an 11-hour model. Into a minutely model. There's lots of ways of doing this, but 11 hours is going to be 11 times 60 or 660 minutes. So do I really want to do that this way though? I don't want this question in here. I'm going to strike that from your notes. Nobody is ever going to ask you to do that. I'm not going to either. All right, so now you're at the U tries. Yeah, so there you are. And there's your half-life notes. We'll probably spend another day doing logarithms with money just to get you guys practice with logs, but we're more or less done with them now.